Okay, I got a couple of questions about number 18, part C. And since this is intended as a review from Calc 2, of the idea of partial fraction decomposition, I wanted to do it together. This is just a first pass at review. We'll be using partial fraction decompositions quite a lot in a few weeks. So we're just starting to refresh ourselves on what it means to do a partial fraction decomposition. So we're starting with this equation dy dt equals y squared minus 3y. And because it is autonomous, we can separate it. So we rewrite it so that we have 1 over y squared minus 3y dy equals the integral dt. Okay, so on the left-hand side, this integral is a rational expression. And if we try out things like u substitution, we don't get anywhere. And so the technique we're going to be using is really helpful if we can factor the denominator up. In this case, it factors as y times y minus 3 dy. Okay. So the goal is to try and rewrite this fraction as the result of doing a sum or a difference of pieces that have common denominator y times y minus 3. Okay, so we're going to write this out on the side. So what we're going to try and do is find unknowns a and b so that these fractions a over y and b over y minus 3 sum to give you 1 over y times y minus 3. Now this is a sensible idea, because if we were trying to find a common denominator between these two terms, multiplying the two terms together gives us a good common denominator. Okay, so our first step is we're going to just clear out this fraction y times y minus 3. So we see this denominator here. We're going to multiply top and bottom. We're going to multiply both sides of the equation by y times y minus 3. Okay, so that leaves us with a cancellation on the left side. So we have a 1, and on the right hand side we have a times y minus 3 over y plus b times 1 times y minus 3 over y minus 3. All right. Now there's a little bit of simplification we can do here. The y's cancel in the a term, and the y minus 3's cancel in the b term. Okay, and so we get 1 equals a times y minus 3 plus by. And we want to now solve for a and b. So there are two important strategies. So strategy 1 is going to be to rearrange things, rearrange the right side so powers of y are grouped together. Okay. All right. So for example, here we have 1 equals ay minus 3a plus by. And we can rearrange this so that we have a plus by minus 3a equals 1. And these are supposed to be equal as functions. So this left-hand side is actually 0 times y plus 1. And if we're comparing these polynomials, they have this equal constant terms. So we end up with an equation that 1 equals negative 3a. Oops. And we also get an equation that 0 equals a plus b. Okay. So this tells us that a is -1/3. And plugging that a into the second equation tells us that 0 equals -1/3 plus b. So b is equal to 1/3. Okay. So this is one strategy. It is especially powerful when we see things like repeated roots or quadratics. Next, we're going to solve the same problem, finding a and y that make this true. But this time we are going to try evaluating our expression at different values of y. In our second strategy, what we're going to do is think of these as functions that are equal to each other. And we're going to evaluate both sides at convenient y values. Because these functions are equal to each other, we actually have equality no matter what values we want to put in. So we could put a whole bunch of different ones in. But particularly helpful for us is going to be evaluating these at the roots of y minus 3 and y. So let's try plugging in y equals 3 and see what happens. So on the left-hand side, when we plug in, there's no y's there. So when we try plugging it in, we just get a 1. And on the right-hand side, when we try plugging it in, we get a times 3 minus 3 plus b times 3. And so this simplifies down to just being 1 equals 3b. And so b equals 1/3. Okay, so we were choosing the y value that made y minus 3 equal to 0. Let's also try plugging in y equals 0. All right, so we evaluate on the left-hand side, and since that doesn't have any y's, it just gives us 1. On the right-hand side, we have a times 0 minus 3 plus b times 0. We actually know what b is, but that term just goes away. And so we have 1 equals -3a. And so a is -1/3. Again, we were choosing this value just to make the term y equal to 0. Okay, well, whichever strategy we use, we now have a decomposition. We know that 1 is equal to -1/3 times y minus 3 plus 1/3 times y. And so what that told us was that 1 over y minus 3 times y was equal to, let's go back to our original decomposition. This was a over y plus b over y minus 3. So our a here was -1/3 over y plus 1/3 over y minus 3. And instead of writing a fraction as our numerator, you can always just write it out front. Now, the power of this is that these new pieces are a lot easier to integrate. In fact, we can do this integral right away. So on our left-hand side, I'm going to just pull out this factor of 1/3 out front. On our left-hand side, we have -1 over y plus 1 over y minus 3 dy. And on our right-hand side, let's go back up, we just had integral dt. Okay. All right. So both of the integrals on the left-hand side give us natural logs. So the first one we can do directly. This is negative the natural log of the absolute value of y. The second one, we do a tiny little u sub if u equal to y minus 3. And that gives us natural log of the absolute value of y minus 3. And the right-hand side here, we have the integral dt, which gives us just t plus. Okay. All right. If we wish to, we can combine these two natural logs together. Right. So we have a difference log of y minus 3 minus log of y. So it's going to turn into a quotient. So y minus 3 goes on top, and then y goes on the bottom. And we can combine them into a single absolute value because we're looking at a quotient. You could also do that with a sum. Okay. We are going to multiply across by 3. And so this gives us log of absolute value y minus 3 over y equals 3t plus c. All right, so here we are in an implicitly defined format. We can put this into Desmos if we're interested, and I will put that graph here. So if you click on the OneNote link here, you'll be able to open this graph up. The red curves represent the solutions to this implicitly defined function, and you can try moving around that c value to see how it shifts your solutions around. We can solve for y here. We're going to exponentiate both sides. That's going to undo the logarithm over here, and we have absolute value of y minus 3 over y equals e to the 3t plus c, which is e to the 3t e to the c. So keep in mind, e to the c can be any positive value, and we've taken absolute values. So we can actually drop these absolute value signs and replace our expression with an a e to the 3t, where a here is any real number. And we found two equilibrium solutions, y equals 3 and y equals 0. All right, so if we want to go forward, let's divide. Well, we have a couple of options. So one thing we could do is multiply both sides through by y. Yeah, let's do that. So we get y minus 3 equals a e to the 3t times y. We're going to solve for y now. So we have 1 minus a e to the 3t times y equals 3. So we're just subtracting this y term over to the left side, adding the 3 over to the right, and then factoring out y. Actually, let's add one step just showing partway through this process. Okay, so we're going to subtract this a e to the 3t times y over, then add 3 to the right-hand side. Because we have that common factor of y in both of these terms, it can be factored out. Okay, and so we get that y equals 3 over 1 minus a e to the 3t. Alrighty, great. Okay. Now there are a couple of things that we can see if we're looking at this solution. Right, we also have, we have a couple of equilibrium solutions. We have y equals 3 and y equals 0 that aren't represented. Oh, well, y equals 3 is represented if a equals 0, but y equals 0 is definitely not represented here. So let's add that in as an additional solution. Alrighty. Now, based off of our phase line, remind you of what that looked like. We had 0 and 3. And we found that 3 was unstable and y equals 0 was, let's just double check that. Yep. Okay, yep, we found that 3 was unstable, that y equals 0 was stable. You might be interested in looking to see what's happening to your long-term solutions. Now, if we were just to take the limit as t goes to infinity, the only limit we get out here is y equals 0. And so you might ask, like, what's going on with these sorts of solutions that are supposed to go off to infinity? All right. Well, these represent solutions where we have vertical asymptotes. So if A is greater than 0, then 1 minus a e to the 3t equals 0 for some t. So for t, let's solve this. 1 over a equals e to the 3t. So we have that the natural log of 1 over a times 1/3 is that t value. So we'll have a vertical asymptote at this t value. And so instead of being able to actually take the limit as t goes to infinity, our solution will go to infinity on a finite interval. So we're going to have a vertical asymptote here. Okay. Great. So some of the things that I was hoping you would get out of this, just a review of partial fraction decomposition. In this case where we have non-repeated linear roots. And a little bit of practice of working with natural logarithms and exponentials. Great, thanks.